This session is for OCR FP2, the topic is hyperbolic functions, and we're going to be looking at question 9 from January 2010. So just having a look at the question in full, first of all. Part 1, given that y equals the inverse tanh of x for x between -1 and +1, we've got to prove that y equals a half log of 1 plus x over 1 minus x. And then in part 2 it says it is given that f of x equals a cos x minus b sin x, where a and b are positive constants. And then part A says given that b is greater than or equal to a, show that the curve with equation y equals f of x has no stationary points. And in part B, in the case where a is greater than 1 and b equals 1, show that f of x has a minimum value of root a squared minus 1. So let's make a start at part 1. So we're given y equals the inverse tanh of x. So that means that x is equal to tanh y. And using the definition for as tanh is sine over cos, that will mean we will have e to the y minus e to the minus y over e to the y plus e to the minus y. So the halves obviously cancel out. We could multiply that now, top and bottom line, by e to the y, so we end up with x equals e to the 2y plus 1, minus 1, that should be, of course, shouldn't it? Minus 1 there. So that's a minus, and on the bottom line it's e to the 2y plus 1. So I'm now just going to multiply out to get rid of the fractions. So we'll have x upon e to the 2y plus 1 equals e to the 2y minus 1. And multiplying out the brackets and rearranging it, that will give us 1 plus x equals e to the 2y upon 1 minus x. So now we can say e to the 2y is equal to 1 plus x over 1 minus x. And you can see we're getting there, which in turn means that 2y equals log of all that, which means that y is equal to a half log of 1 plus x over 1 minus x. So we have established the result, and you have to be careful because of course we're given the answer, so we just need to show that we do it clearly. So at this stage we will get a statement mark for using the definition of tanh being sine over cos. We'll get a method mark here for substituting in and rearranging our equation at this sort of stage here, and then just an accuracy mark for making sure that we can work through the algebra and show that we get the required result. So let's have a look at part 2 and see what we were looking at there then. So in part 2 it says it is given that f of x is equal to a cos x minus b sin x, and we're also told that b is greater than or equal to a, and we've got to show that there are no stationary points. So f of x equals a cos x minus b sin x. So we're dealing with stationary points, so we'll want to differentiate. When we differentiate cos, we get sin, and when we differentiate sin, we get cos. So now we have our first derivative. If we had a stationary point, so for a stationary point, we would have f dash of x is equal to 0. In other words, that would mean that a sin x would be equal to b cos x, in which case tanh x would be equal to b over a. Now we're told that b is greater than or equal to a, which implies that b over a will be greater than or equal to 1. But the trouble is, tanh, the graph of tanh, as we should know, goes, the tanh function will be between -1 and +1. Well, we're not so worried about that bit, but it's this bit that we're interested in. So the tanh graph would always be less than 1. So in fact we have an inconsistency here, so it isn't possible, and therefore the only conclusion is that we have no stationary points. So there were 3 marks for that. So again, just checking on where those marks are given. You got a mark for differentiating and putting it equal to 0, and an accuracy mark for getting an expression for tanh. You then got a statement mark, a B mark, just for justifying the fact that in fact you can't have, it'll never be equal to 0. And that's the important thing there, that it can never be equal to 0, and therefore you can never have a stationary point. So now we move on to part B, and in part B we've got a fair bit of work to do here. It says, a slightly different case, because here we're told that A is greater than 1 and B is equal to 1. So the first thing that we need to see, of course, if this A is greater than 1 and B is equal to 1, then that implies that in fact that we could have a stationary point. So a stationary point will exist in this particular case. It is possible, because of course b over a will be less than 1. So that fits in with our graph. The tanh of x, instead of being b over a now, since b is equal to 1, it's going to be 1 over a. So that implies that we have the tanh, inverse tanh of 1 over a will be equal to x. And that means that if we take the inverse tanh, so that implies that x is going to be, now we're going to use the log definition that we were looking at right at the beginning of the question, part 1. So that means that x equals a half of log 1 plus 1 over a all over 1 minus 1 over a. So we're just using the result from part 1 with x replaced by 1 over a. So we could, of course, just looking at that, we could take a common denominator of a on each of the numerator and the denominator, which will then give us x equals a half of log a plus 1 over a minus 1. So we now have a value for x. So what we need to do is to substitute it in now to our function. So we know the function f of x, which is a cosh x minus b sine x. So now that's going to become a cosh. Instead of having x, we're now going to have all of this. So it's going to be a half log of, and I'm going to write this just as a fraction like that. So that's a half of log a plus 1 over a minus 1 minus sine. So remember b is equal to 1, so sine of x is going to become sine of a half log of a plus 1 divided by a minus 1. Need another bracket. And what we need to do now is we need to use the fact that we have the definition for cosh. The cosh function, remember, cosh of x is a half of e to the x plus e to the minus x. So we're now going to put this in exponential form, and of course once we do that we're going to be using the inverse property of exponentials and logs. So it's a half of e to the x plus e to the minus x, so I'll take that half out, so it'll be a over 2. And now what we're going to have is we're going to have e to the power of all of this, so it's going to be a half log of a plus 1 divided by a minus 1 plus e to the minus of all of that, and then we'll do the same for shine, remembering that that means we'll have a half outside, and shine has a minus sign, so it'll be e again to the half of log a plus 1 divided by a minus 1 minus, this time, e to the minus a half of log a plus 1 divided by a minus 1. So that doesn't look very nice at the moment, but if we remember that exponentials and logs are inverse functions, we should be able to simplify it. So let's have a little look. So I've written that up again here. So again, if we think about the fact that we could take this half and write it as a power, then we'd have e to the power of log a plus 1 over a minus 1 to the power of a half. So we could actually then write that as a over 2 upon a plus 1 over a minus 1, and they'll both be to the power of a half. So you could either do that singly or like that, it won't matter. Similarly for this, we're going to get a minus 1. It's to the power of minus, so that means we're just going to be inverting those. So it'll be a plus 1, again both to the power of a half. And that, we still have the a over 2 outside the bracket. And then we'll do the same thing over here. We'll have a plus 1 to the power of a half over a minus 1 to the power of a half. And this time it's a minus, so it'll be a minus 1 to the power of a half over a plus 1. So again, it still doesn't look great, but we're getting there, because what we need to see now is that we could take a common denominator to add these two fractions or subtract these two fractions over here. The common denominator will be a minus 1 upon a plus 1, which of course is a squared minus 1. So we've still got the a over 2. So we've got this common denominator now of a squared minus 1 to the power of a half. So a minus 1 will go into that a plus 1 times, and you'll to the half, and you'll multiply it by this a plus 1 to the half, so you get a plus 1. And then the same here, you're going to get an a minus 1. And we'll just follow the same sort of thing through over here, but we just have to be careful because of course there's a minus sign here, so we'll get an a plus 1 minus a minus negative 1, so that's a plus 1. And again that's a squared minus 1 to the power of a half. So what have we got now? And we're just about there, because here we have 2a, and the 1's cancel out, so the 2a and the 2, that 2 cancels out, so we'll get an a squared all over a squared minus 1 to the power of a half, and over here the a's cancel out and we get a 2 which cancels out with that 2, so this is just minus 1 over a squared minus 1 to the half. And we've got, we're subtracting fractions which have got the same denominator, so that means we end up with a squared minus 1 over a squared minus 1 to the power of a half. which of course we can divide through now by a squared minus 1 to the power of a half, and that gives us a squared minus 1 to the half, or as they've said in the question, the square root of a squared minus 1. Now the last part of the question is important, but if we just go up and have a look at our function here, if we differentiate it twice to find the second derivative, then the second derivative is actually just going to be the same as the function itself. And because of that, that means that the second derivative is going to be equal to the square root of a squared minus 1 as well. And of course we know that that is greater than 0. And so we can confirm that it is a minimum. So quite tricky there, I think, that part B. And there were just 6 marks for it. So if we just have a look and see where the marks actually came from. So if we go back to the beginning, so first of all, the important thing here was that we had a mark for seeing that tanh x was going to be 1 over a, and then we got a method mark and an accuracy mark here for getting x in terms of this, in this form, a half log of a plus 1 over a minus 1, or some equivalent form. It may not be in that exact form. The next sort of mark that we got was for this bit here, where we were able to go from the to see that exponentials and logs were inverse functions, and so we were able to simplify it here. So there was a method mark here, and then another accuracy mark for showing that it was root a squared minus 1, and a statement mark for confirming that it was a minimum. So as I say, quite a lot of work for some of the marks here. But in total, we had 6 marks for that part, and we had, if we go back, we had 3 marks for part 2 and 3 marks for part 1. So 12 marks in total for the question. So don't forget that if you want to look at further revision videos, then you can do so by going to the Further Maths Support Programme website and following the link.